Hi everyone, my name is Marcio Batista, and this is my talk to the Geometric Analysis Past, Present, and Future Season 2 event. I will talk about minimal hypersurfaces with low index in the real projective space. First of all, I would like to say that this talk is based on a work with Matheus Martins. So, the first part of the talk, I will recall some notations and some basic results. In this first moment, I will introduce the following notation. I will consider immersion of sigma in M. Sigma is a compact two-sided hypersurface in M. I will denote by N the unit normal vector field along sigma, and by A its Van operator associated to the immersion. And finally, the mean curvature function is the trace of the Van operator. Okay. Next, recall that each smooth function f on sigma induces a normal variation, which I will denote by xt, and this variation has a explicit formula. It is given by the exponential of m, by this expression in the slide. Okay, and use this variation, we have several copies of sigma in M, and we are able to compute the area of these hypersurfaces. And the formula for it is given by this integral on sigma. Sigma t means the manifold sigma with the metric induced by xt, and dvt is the Riemann volume induced by such metric. Okay. The first thing I would like to introduce is the notion of minimal hypersurfaces. This notion is associated to the mean curvature, and you say that the manifold sigma is minimal with respect to this immersion X if its mean curvature vanishes along of sigma. Okay. And next, I will recall the first variation formula and notice that being minimal is a variational property. So the first variation formula is given by this expression, is the integral is minus the integral of f times h, and it is simple to see that this expression vanishes if and only if the mean curvature is 0. So minimal hypersurface is a critical point for the area functional. Okay, it's very direct from this formula. Okay. Next, since a minimal hypersurface is a critical point of the area, it is natural to think about what sort of critical point is it. So for understanding the kind of critical point it is important to know the second variation of the area. And because of that, we recall this formula, which is known by second variation formula, and associated to this formula we have an elliptic operator J. J is the Laplacian plus two terms. These two terms it is associated to the extrinsic part of sigma in M and the curvature of M along sigma. So the normal square of A is just the trace of the operator R square, and reach bar means the reach curvature of M. Okay. Such operator on a compact manifold has a discrete spectrum. So you can associate the variations, the normal variations, which decrease area, with the number of eigenvalues of J, which are negative. This content is in the next slide. First, to recall what I already said. The sequence of eigenvalues of J is a non-decreasing sequence going to infinity, and the first eigenvalue is simple. It is a well-known result in PDEs. So, for us, it is interesting to know how many directions you can perturb the hypersurface sigma and decrease the area. Such directions are associated to the negative eigenvalues of the operator J. And if you count the number of such eigenvalues, negative eigenvalues, we'll have a quantity which we call index, Morse index of the hypersurface sigma. Okay. Such number has a geometric interpretation, as I had said. So finally, we say that sigma is stable if its index is 0. Now, I will recall some important results in the literature about estimations or computations of the Morse index of a minimal hypersurface in some interesting manifolds M. And I will recall the first one is a beautiful result of James Simons. This is part of his PhD dissertation. It's a small part of the thesis. And the theorem says there does not exist stable, compact minimal hypersurfaces in the unity round sphere. Moreover, the totally geodesic sphere are the only compact minimal hypersurfaces with index 1 in the unity round sphere. So he was able to describe, to characterize the hypersurfaces in function of its index. So it's a beautiful result. Very, very interesting computations using until now. So I will now bring attention to the second result about the still about the stability or, or index low index. The next result I would like to present is this theorem due to Shen Yao. This theorem is very general. You assume just a geometrical hypothesis on the ambient, but you need to do this for dimension 3, only for dimension 3. In high dimension, such a result is not so direct like that. You need other hypotheses, other conditions. So the theorem says that if M is a completely oriented three-manifold with non-negative scalar curvature, and you have sigma in M, a oriented compact stable minimal surface, then sigma is conformally equivalent to the sphere, or sigma is a totally geodesic flat torus. So they were able to say the topological characteristic of the surfaces. In the case of genus 1, you are able to say something more. You say that the hypersurface is totally geodesic and flat. Okay, so it's a beautiful result. I point out just this result because I'm interested in this talk about compact hypersurfaces. But 1 year later, Fischer, Kobre, and Shen studied the case of complete hypersurfaces, and they characterize in a similar way of this theorem too. So next, we would like to present a beautiful result of Urbano. Urbano studied minimal hypersurfaces in S3 in the unilateral sphere of dimension 3, and he proved a gap of the index and characterized the number which is present in the theorem. So the theorem says that any compact minimal non-totally geodesic surface in S3 has index at least 5, and the equality occurs only for minimal Clifford surfaces. So this is a beautiful result. You have a gap. You in this sphere you don't have stable hypersurface. The next one is the totally geodesic sphere that has index 1, and after that you have the Clifford torus with index 5, and any other one has index greater than 5. So it's very nice, this result, and this result is still open in high dimensions. So Sophie proved this result, this gap in high dimension. He proved that sigma n immersed in Sn plus 1 has index at least n plus 3, but he can't prove what occurs in the equality. There is a conjecture that says that the only hypersurfaces with index n plus 3 are the Clifford hypersurfaces, minimal Clifford hypersurfaces. But this is a open problem yet. So continue. Would like to present some more results, but the literature is very very large, so I choose just more two results. The first one is a theorem uh, of do Carmo, Ritorei, Ross in 2000. In this paper, they prove, in this paper they have done in 2000, they prove the only compact two-sided minimal hypersurfaces with index 1 in the real projective space are the totally geodesic spheres and the minimal Clifford hypersurfaces. It's a nice result. He, they was able to describe exactly the hypersurface with index 1, and this is in my point of view, this is the second more simple space to work, because I think the first one is the sphere and the second is the quotient of the sphere, which is more simple quotient of the sphere, which is the projective space. But in the projective space, the, the results are very hard to work, but they was able to compute the index of the torus and proved that the torus are the torus and the total geodesic spheres are the only one with index 1 in this space. So, continuing. Finally, we recall a result due to Ambrosio, Carlotto, and Sharp. Is a very young result, just 4 years. And the theorem says that for any closed embedded minimal hypersurface, sigma of a compact rank 1 symmetric space holds the index of the minimal hypersurface is greater than a constant times the first bit number of the hypersurfaces. It is a very nice result. The geometric interpretation you have is that if you have a lot of topology in this hypersurface, the index is very large. That says the instability is very large. Okay, but this result is qualitative. You don't have a good consistency in this theorem. Okay, I would like to point out that in the literature you have many results about index in some sense for other settings, like the CMC, the setting of CMC, constant mean curvature hypersurfaces, or weighted hypersurfaces, or solitons, self-shrinks of the mean curvature flow, for example, and the others. Many other situations, variational problems, which you are able to study something similar to index in such settings. So this is a very nice subject and very fruitful. Finally, to conclude the first part of the talk, I will introduce some notations which will be very useful for me in the second part of the talk. Okay. The first thing I will fix is I will work just with hypersurfaces in the projective spaces, but the sphere is the true cover of the projective space, so it is very natural. I introduce notations related with the sphere. So for us, X will be an immersion of a compact-oriented minimal hypersurface in the sphere. And HV will be the high function in direction V, and FV is the angle function with the direction V, where V is a vector, a fixed vector in the Euclidean space. Finally, I recall a very interesting vector field along the hypersurface sigma. This vector field was first studied by Do Carmo, Hittore, and Royce, and a few years later, Celso Viana also studied this vector field in the case of isoperimetric problems in the projective space. It's a very beautiful paper of Viana. Next, using this notation, after direct computation, we have the following results. The Jacobi operator of this vector field phi is given by this expression. Okay. Of course, the Jacobi operator of a hypersurface acting on smooth functions as phi is a vector field in R n plus 2, you can compute the Jacobi operator of each part of the vector field, the first, the second, until the last one, the n plus 2 position. And you can write everything in the vectorial form because it's more simple that way. And for this vector field phi, you have J of phi equal to this nice expression. This nice expression will be very useful later. The second lemma we have is the index of this vector field, which is defined by this expression in the second lemma. If you compute the index of phi AB, you have this integral, very simple, which are very nice for us in the following computations. Okay. I would like to notice that if the norm of the second fundamental form is constant, then you can put outside of this integral the norm square minus n. And you have a simple expression in the integral. Okay, I would like to stop now. I will see you in the next part of the talk.